in this section, I want to talk about ordered symbol tables, which is really why binary search trees are good. I'll come back to this in a second. Ordered symbol tables is an extension of the abstract data type of a symbol table. It has all the operations that you've just seen before, but it has a few more that come in handy. In particular, you're allowed to find the smallest and largest key. You can find something that's called floor and ceiling here. Yeah, if you're given a key, you can find what is the largest key that's smaller that is in the data structure that is contained in the dictionary, or the largest that is smaller. Sorry, that's what I just said. Or the smallest that is bigger. So same, like think of floor as being on the set of all integers. You can ask for any real number. What is the floor? That is the biggest integer that's smaller than that real number, less or equal than that number. Okay, that's the definition of floor. And ceiling is similar. And you can do this in general in a ordered symbol table. Now you might wonder why this is useful, but suppose you have a dictionary storing English words. Then, for example, a crappy spell checker could say the thing you typed is not in the dictionary. This is not a proper English word. But look, there's one that's close in the alphabet to what you typed. Maybe that's what you meant. That might be. It's not a good way because probably you make a typo also in the first few letters, and that wouldn't be caught by this. As just one example. The last two look even more esoteric, but are actually very, very essential for a core abstraction that I'll come to. And you can read about it below. So rank of a key is the number of keys that are stored in the symbol table that are strictly smaller. So in a sense, it's if I were to insert this key, the house, how many smallest the house, if I would insert it, then it is the rank xth smallest, terrible, in the data structure afterwards. And select is the opposite. I can tell you I want the 42th smallest from that symbol table, and you would give it to me. That's those two operations. Why do I think that these are really essential? You can think about those as implementing an array where you can insert at any point and at any position without copying elements around. The rank just serves the purpose of an index. And by select, you can jump to any position in the sorted list without really having to have it in one contiguous piece of memory. And in that case, yeah, you might even do away with the keys if you wanted. You could just represent the keys implicitly, but that's, yeah. So this is a way to implement a string, which is a list of characters, right? Where you can add a little bit of text at any position. This is, or at least used to be, the data structure that text editors were using. If you maybe thought about this at some point, there's text editors where you can type along and then save your text. They have to represent the content of the text file somehow. And one way to do this is like this, where you store the text in a big binary search tree, and then at any point you can insert wherever the cursor currently is, you can insert at this point without copying everything around. Now, I think modern text editors use a slightly simpler data structure than this because they figured out people are not using text edits in an adversarial way, and there's cheaper ways to do it. But from the abstract point of view, a binary search tree is a good way to do it. Another point I want to make here is if you don't need the ordered operations, if you just need the symbol table, you might actually want a hash table in practice. A hash table is a different way to implement a symbol table that we will not talk about because I couldn't fit it in this class along all the other things. but you should really know what a hash table is if you want a computer science degree, so maybe you want to read it up. And this is also the way how Python implements its built-in dictionaries. They're hash tables, which means Python dictionaries cannot really efficiently do these things. If you need that, you need a different implementation of dictionaries. But like in this truly dynamic array, or this rope data structures for strings, that's what it's called if you use it for a string. It's a name people coined. I don't know if it's a good name, but it is a name. Then you need really an ordered symbol table. Okay, let's see if you paid attention. Here's a little example. I just want to see if you have the definition in your head. What is rank of 35? I hope it's just big enough. So 35 is here, right? $11. There's a few more people in here. Should I rather show the tree again? You have to tell me if I'm asking you to work on an example that you can't see anymore. All right. We have lots of votes in, and it seemed fairly clear, so let me show this. You could see the last one. So 4 is, yeah, I know you keep changing your votes, don't you? Let's briefly see why 4 is the right answer. Remember that we draw binary search trees so that the keys nicely project in x direction, well, project in y direction onto the x-axis in sorted order. So this is the smallest, second smallest, and so on. So this would have rank 0, 1, 2, 3, 4, because there's 4 keys that have a keys smaller than 35. All right? That was what rank does. The nitpick here maybe is that it asks for strictly smaller. You could argue with me whether you want less or equal here or strictly less. Depends what you want, depends on the application, but that was my definition for now. Now you might think about how can you implement these operations, rank, select, and their other friends, in a binary search tree. And it turns out with the binary search trees that we had so far, you can't really do it. Instead, what you need is what people call an augmented binary search tree. And the augmentation on the slide is just, there's a little number floating around each node. So we add another field to every node. And the field that we add is the subtree size. That's the number of keys that are below this node, so the number of descendants, including the node itself. So for example, all the leaves have 1. Then this one has 2 because there's 2 below it. This one has 4, and you can check that hopefully the others are all correct as well. Now, how does that help in answering these operations? Let's see how we can do rank, and maybe we do the same again as an example, 35. How can we work out the rank of 35 without looking at the tree in its entirety? Remember, what we want to do is just follow one path. We don't want to read all those nodes. The running time should still be dominated by the height of the tree. not the size of the output, not the number of keys that are smaller. So the way to go, as always in binary search trees, is we start with a find until we reach this node 35. Now there's a few things to look at. We want to count the nodes that are to the left of this node 35. And there's two types of such nodes. There's those that we explicitly touched when we were moving down our search path. There's two of these, so we can count to two of already. We know that whenever we took the right child pointer, we know we have to add one because the node we've just left is one of those to the left of the final target. But there's more. There's the subtrees that we omitted here. Now, how can we count those? In this case, it's just one node each, but it could be much bigger. So what we do is we peek into this subtree and get its size from the root. Because every node stores its subtree size, it's enough to go this one step off the path to know how many nodes have we skipped by taking the right pointer in this case. Sorry, right for you. OK. And so here, if you sum up, we have two red things that we skipped and two green pointers two green nodes that we skipped. That makes up 4. And that's the rank of 35. Make sense? So maybe just one, that this is on the slides as well. And so we can get the sizes of, we need the augmentation for getting the size of these red subtrees that we skipped in constant time as opposed to walking along the tree and counting. We can also do select in a similar way. It's a little more subtle maybe. Let's do the same one. We want to find 35 again. So we want to find the element of rank 4. How do we do this? We start at the root as always. We do our search. Now, I need to know whether I have to go left or right. And here the trick is we have to go a little detour. We know that this node overall has 16 nodes below us, but that doesn't tell us how many are left and right. Instead, though, what we can do is we take a look at the left child's subtree size. And this says 9. So there's 9 elements to the left of this. And we compare this with our rank. Our rank is 4. We want to find the element of rank 4. And there's 9 things in the left subtree. That means we have to continue in the left subtree. Yeah, I keep getting confused because it's mirrored for you. Now, here again, we know that this guy has many things below in its subtree. But what we really want to know now is, do we have to go left or right? So at this point again, we peek into the subtree and get the 1, which tells us there's only 1 in the left. That's too small. We want the 4th. So we have to go right. Now, so far so good. But now it gets a little tricky. Because if we go into this subtree, we have actually cut off 2 nodes. So in the subtree, we are now looking at rank 2. We no longer look for rank 4. That was for the global tree. We've excluded 2 nodes already. So we have to adapt our rank. We have to subtract the nodes that we skipped. But again, we know how many because there's the 1 on our path, and we get the size of this subtree from looking into the child. So we can calculate what rank we're recursing on. So one more step, and I'll do it a bit quicker. So here we check this guy. This is big enough for rank 2, so we go to the left. And here we peek into this one. 1 is too small. So if this one is 1, then actually rank 2 is to the right. But now we have, again, 2 nodes that we have to exclude. So here we excluded these 2, here we excluded these 2. So we recurse on this node, on this subtree, but now we want to find the node of rank 0 in this subtree. And well, because this one doesn't have a left child, the root is at rank 0. And so we return the root, which is 35. Okay? I know this is the most subtle of the algorithms that we looked at, because you have to adapt the rank while you're going. But it's the same concept as before. You just exclude some nodes and you can calculate how many you excluded. Now, I've shown you the final solution, how you can augment binary search trees. You might wonder, because I was talking about ranking select, why don't we just store the rank of every node in each node? That would have made life much simpler, much easier, and we wouldn't have needed this weird adapting the rank and all that nonsense. Now, you could try to do this, but you can't maintain it. If you insert an element, think about it as follows. So we have a little tree. So there could be a huge subtree to the right here. And now you add a new element here on this side. Then the ranks of all those guys change. And there's just no way how we can possibly visit all those nodes in the short time we spent on walking down this search path. We can't visit every other node in the tree and update its rank, add 1 to the rank. So that won't work. So that's the reason why we go for subtree sizes instead, because the subtree sizes of all these guys is not changed if we insert something in another unrelated part of the tree. And on the other side, all the nodes whose subtree size changes must have been on the search path, because something changed below them, so we must have come across them while we were searching for the node in the first place. So we can definitely, in order H, we can go and update them all.